Northrop Grumman's digital engineering revolution begins here. Advanced virtualization eliminates physical prototyping, allowing engineers to simulate structural integrity and aerodynamics before a single piece of metal is cut. The digital twin concept serves as the B-21's backbone. This cloud-based environment ensures every subsystem integrates perfectly, reducing lifecycle costs and significantly accelerating the critical acquisition timeline. Entry into Plant 42 requires top-level clearance. Biometric scanners and layered security protocols protect America's most sensitive stealth technology from unauthorized access and foreign espionage threats. Raw carbon fiber spools arrive in temperature-controlled shipments. These precursors are the foundation of low-observable composite skins, requiring strict environmental stability to maintain their structural properties. Aerospace-grade titanium ingots undergo rigorous purity testing. This high-strength alloy provides the Raider's skeleton with essential heat resistance and durability without compromising the aircraft's critical weight targets. Automated laser cutters slice through composite plies with micron-level precision. This nesting software maximizes material efficiency, significantly reducing waste while ensuring exact fiber orientation for structural strength. Massive Invar tooling molds are prepared for the layup process. These thermally stable forms ensure that composite parts maintain precise dimensional accuracy during high-heat curing cycles. Skilled technicians hand-place initial composite layers. While automation is key, human expertise ensures complex geometries adhere to strict tolerances required for next-generation stealth performance. Automated fiber placement machines take over for large span sections. These robots deposit carbon tape at high speeds, creating a seamless, void-free structure essential for durability. The composite assembly is sealed within vacuum bags. Removing air pockets is critical, as even microscopic voids can compromise structural integrity and radar cross-section performance. Massive autoclaves apply heat and pressure to cure the composite parts. This chemical bonding process solidifies the resin matrix, transforming flexible fabric into rigid, flight-ready hardware. Cured components are carefully removed from their molds. The parts now exhibit the high strength-to-weight ratio necessary for long-range strategic bombing missions in contested airspace. Non-destructive testing utilizes ultrasonic waves to scan for internal defects. Inspectors analyze the results to guarantee that every square inch meets the Air Force's rigorous standards. 5-axis CNC machines trim the composite edges. The diamond-tipped cutters carve complex contours, ensuring that panels fit together with the tightest gap tolerances in aviation history. The internal aluminum and titanium rib structure is assembled. These ribs form the aircraft skeleton, designed to absorb aerodynamic stress while supporting the flying wing's unique shape. Robotic drilling units bore thousands of fastener holes. Vision systems align the drill bits perfectly, preventing delamination and ensuring distinct aerodynamic smoothness on the exterior skin. Technicians install flush head rivets into the airframe. Each fastener is coated in sealant to prevent galvanic corrosion and maintain the continuous electrical conductivity of the skin. The main wing spars are lowered into position. These massive beams carry the primary load, connecting the fuselage to the wings and housing the integral fuel tanks. Workers apply sealant to the interior fuel boundaries. This meticulous process ensures leak-proof containment for the extensive fuel load required for the Raider's global reach capabilities. The central keel beam is installed. This structural spine supports the weapon bays and landing gear, acting as the primary load path for the aircraft's heavy payload. Serpentine inlet ducts are integrated into the fuselage. Their complex shape hides the engine face from enemy radar, a critical design feature for deep penetration stealth missions. Heavy-duty titanium engine mounts are bolted to the airframe. These structures must withstand immense thrust loads and thermal cycling while isolating vibration from the sensitive avionics. The upper and lower fuselage shells are mated. This clamshell assembly requires laser-guided positioning to ensure the aerodynamic profile remains perfect for low-drag flight performance. Laser trackers verify the dimensional accuracy of the joined fuselage. Any deviation from the digital model is corrected immediately to maintain the outer mold line integrity. Internal avionics racks are installed in the forward bay. These modular chassis are designed for open systems architecture, allowing for rapid software and hardware upgrades later. Miles of Kapton-insulated wiring are cut and labeled. These harnesses form the aircraft's nervous system, transmitting data and power to every sensor and flight control surface. Technicians weave wires into complex looms. Shielding is applied to protect signals from electromagnetic interference, ensuring the fly-by-wire system operates without error in electronic warfare environments. The wiring looms are routed through the airframe. Clamps secure the bundles to prevent chafing, a critical safety step to avoid electrical fires during combat operations. Titanium hydraulic lines are bent and fitted. These high-pressure systems power the flight control actuators, providing the muscle needed to maneuver the heavy bomber at speed. Environmental control system ducts are installed. These manage cooling for the avionics and crew, managing heat signatures, which is vital for maintaining infrared stealth characteristics. Thermal acoustic insulation blankets are wrapped around the fuselage interior. This protects the crew from engine noise and stabilizes the internal temperature for sensitive electronic equipment. Firewalls are installed between the engine bays and fuel tanks. These safety barriers are constructed from fire-resistant titanium alloys to contain catastrophic failures during combat scenarios. Massive steel trunnions are bored out. These mounting points will hold the landing gear, transferring the shock of landing impacts directly into the main wing structure. The pressure vessel for the cockpit is lowered in. This composite tub maintains a breathless atmosphere for the pilots during high-altitude operations near the stratosphere. Ejection seat rails are aligned and bolted down. Precision alignment ensures that the escape system functions flawlessly, providing a safe exit vector during emergency egress scenarios. The main instrument panel frame is attached. This skeleton will house the large area displays, serving as the primary interface between the pilots and the intelligent machine. The cockpit glare shield is installed. Its geometry prevents internal light reflections on the canopy, preserving the pilot's night vision and maintaining external light discipline. Adjustable rudder pedal assemblies are fitted. These flight controls link directly to the digital flight computer, translating pilot inputs into complex aerodynamic yaw adjustments. The throttle quadrant is integrated into the console. These controls manage the sophisticated engine cycles, balancing thrust requirements with fuel efficiency and thermal signature management. The titanium frame for the canopy is machined. This rigid structure must seal perfectly against the fuselage to maintain pressurization and preserve the continuous stealth coating. The Pratt & Whitney turbofans arrive in sealed containers. These modified commercial cores are heavily adapted for military use, prioritizing thermal management and high-altitude efficiency over raw thrust. Cranes lower the engines into the buried fuselage bays. Precision alignment is vital to minimize vibration signatures, ensuring the propulsion system integrates seamlessly with the stealth airframe. The exhaust mixing nozzles are attached to the engine rear. These structures flatten the exhaust plume, rapidly mixing hot gas with cold air to suppress infrared tracking. The auxiliary power unit is installed deep within the wing root. This turbine provides independent electrical power and pneumatic pressure for engine starting without ground support equipment. High-output generators are coupled to the accessory drive. The Raider requires immense electrical power to feed its advanced sensor suite and electronic warfare jammers during combat operations. Heavy-duty main landing gear struts are bolted to the trunnions. These robust legs must support the aircraft's increasing gross weight while retracting compactly to preserve internal volume. The nose gear assembly is installed with precise steering actuators. This unit includes sensitive proximity sensors to ensure safe ground handling and automated retraction sequencing during takeoff. Hydraulic lines are connected to the brake assemblies. High-pressure fluid dynamics provide the stopping power necessary to halt the heavy bomber on relatively short, forward-deployed airfields. The advanced rotary launcher is fitted into the central weapons bay. This modular system allows the Raider to carry a diverse mix of nuclear and conventional munitions. Serrated bay doors are hinged to the fuselage belly. The sawtooth edges align with the aircraft's primary radar angles, scattering incoming waves away from the source receiver. Active electronically scanned array panels are embedded in the wing leading edges. These conformable antennas provide 360-degree situational awareness without compromising the aircraft's smooth aerodynamic profile. The wing leading edges are reinforced with impact-resistant composites. This area endures the highest thermal and aerodynamic stress, requiring materials that maintain stealth properties despite atmospheric erosion. Large control surfaces are attached to the trailing edge. These elevons manage pitch and roll, using complex software to compensate for the flying wing's inherent aerodynamic instability. Electromechanical actuators are linked to the control surfaces. Replacing traditional heavy hydraulics with electric motors in specific areas reduces weight and eliminates flammable fluid lines in vulnerable zones. Liquid-to-air heat exchangers are plumbed into the avionics bay. Efficient thermal transfer is critical to keep the massive onboard computing clusters functioning within operational temperature limits. Large-format glass cockpit displays are activated. These touchscreens fuse sensor data into an intuitive tactical map, reducing pilot cognitive workload during long-duration, high-stress strategic missions. The ACE's 5 ejection seats are armed and installed. These 0-to-0 capable seats provide the crew with a survivable escape envelope even from a stationary ground position. The cockpit transparency is lowered and sealed. This specialized glass incorporates indium tin oxide coatings to reflect radar waves, preventing them from entering the chaotic cockpit cavity. The nose cone is attached over the forward sensors. Constructed from frequency-selective materials, it allows the Raider's own radar to pass through while blocking enemy signal returns. The mission computer core is slotted into the avionics rack. This brain processes terabytes of data, enabling the Raider to act as a sensor node in the battlespace. Technicians initiate the smoke test, powering the electrical bus for the first time. Current flows through the nervous system, verifying continuity across miles of complex cabling. The operational flight program is uploaded via secure data link. This software defines the aircraft's behavior, flight laws, and weapon interfaces, representing millions of lines of code. The green aircraft enters the finishing bay. Technicians apply conductive putty over every fastener head, ensuring the skin is electrically continuous to prevent radar wave scattering. Robotic sanders smooth the fuselage surface. Achieving a microscopic level of smoothness is mandatory. Even a paint ripple can create a hot spot on an enemy radar screen. A specialized conductive primer is sprayed onto the bare composite. This bonding layer ensures the subsequent radar-absorbent coatings adhere properly to the airframe under flight stress. Computer-controlled robotic arms move into position. Automation guarantees consistent coating thickness, eliminating human error in applying the critical, highly toxic radar-absorbing materials to the jet. The radar-absorbent material is mixed in a sealed chamber. The exact chemical composition is classified, utilizing magnetic ferrite particles suspended in a polymer matrix. The robots apply the base coat of RAM. This layer is designed to absorb high-frequency radar waves, converting the electromagnetic energy into negligible amounts of heat. The hanger heats up to cure the coating. Precise temperature control is essential to cross-link the polymers, locking in the material's electromagnetic absorbing properties permanently. A top coat is applied for environmental protection. This layer shields the sensitive RAM from rain, UV radiation, and abrasion without interfering with its stealth performance. Technicians apply conductive tape over maintenance access panels. This tape and gap method ensures that removable panels do not break the electrical continuity of the stealth skin. A probe is used to test surface conductivity. The skin must conduct electricity uniformly to dissipate static charge and prevent radar reflections from building up on edges. The canopy receives a final gold-tinted coating. This micro-thin metal layer creates a Faraday cage effect, shielding the pilots from electromagnetic radiation and radar interrogation. High-temperature seals are fitted around the engine exhaust. These flexible barriers prevent hot gases from recirculating into the fuselage, protecting the composite structure from thermal damage. Data ports and pitot tubes are masked off. These sensitive instruments must remain clear of the heavy RAM coatings to function correctly during flight operations. The S-duct inlets are coated by a specialized internal robot. The interior walls must absorb radar waves that enter the duct, preventing them from bouncing back out. Ceramic matrix coatings are sprayed on the exhaust shelf. These materials withstand extreme heat while suppressing the infrared signature generated by the jet exhaust plume. A laser scanner creates a topographical map of the painted surface. It detects deviations in coating thickness as small as a human hair, triggering immediate rework. The aircraft is jacked up for weight and balance calibration. Knowing the exact center of gravity is critical for the flight control computer to maintain stability. The team performs a final solvent wipe down. Removing dust and oils ensures the surface is chemically clean before the final specialized markings are applied. Low visibility national insignia are stenciled using distinct gray tones. These markings comply with international laws of war, while maintaining the aircraft's crucial low observable visual signature during daylight. Fuel trucks hook up for the first wet check. The system is pressurized to verify pump logic and ensure the complex tank interconnects balance weight distribution correctly. Ground power units energize the hydraulic pumps. Control surfaces sweep through their full range of motion, validating the flight control laws and actuator response rates on the ground. The aircraft is towed to a run-up pin. Chocked and tethered, the engines ignite, running through power settings to verify thrust output and thermal management system performance. The B-21 enters a massive anechoic chamber. Engineers bombard it with radio frequencies to ensure internal systems remain shielded and the stealth coating absorbs signals as predicted. Shakers attach to the landing gear struts. They simulate runway harmonics to ensure delicate sensor arrays and avionics mounts do not suffer from resonance failure during takeoff rolls. Software engineers patch the final flight code. This critical update unlocks the flight envelope protections, allowing the test pilots to safely push the aircraft during initial sorties. The hangar doors open for the official unveiling. This calculated media event demonstrates American technological superiority to adversaries while keeping specific design details obscured by lighting and angles. The B-21 Raider is towed into the light. Its unique planform is revealed to the world, signaling a generation leap in strategic deterrence and deep strike capabilities. Immediately following the ceremony, the aircraft returns to the secure facility. Security teams sweep for unauthorized surveillance devices, maintaining the strict operational security required for this asset. Test pilots initiate low-speed taxi runs. They evaluate nose-wheel steering and brake sensitivity, ensuring the digital handling qualities match the simulator predictions on the tarmac. The throttle is advanced for high-speed taxiing. The nose gear lifts momentarily, testing aerodynamic authority and the transition logic between ground handling and flight control laws. Telemetry streams are analyzed by ground stations. Every sensor reading is cross-referenced with digital models, validating the aircraft's readiness to leave the ground for the first time. Senior engineers and Air Force officials convene. They review thousands of data points, signing the executive order that clears the Raider for its maiden flight over California. The test pilot performs the final walk-around. Inspecting the intakes and control surfaces, the human element verifies the machine is ready, trusting their life to the engineering. The canopy closes and engines whine to life. The distinct acoustic signature is recorded, a low rumble that signifies the awakening of America's newest nuclear deterrent platform. The Raider taxis to the hold short line. Escort vehicles follow closely, monitoring for any fluid leaks or smoke that would scrub the mission at the last second. Throttles push to military power. The flying wing accelerates rapidly, generating lift efficiently as the computers make micro-adjustments to keep the unstable airframe perfectly level and true. The wheels leave the concrete. For the first time, the B-21 floats on air, its composite wings flexing upward under the load as it climbs into the sky. The landing gear retracts smoothly into the belly. This cleans up the aerodynamic profile, significantly reducing drag and allowing the aircraft to accelerate to its climb speed. An F-16 chase plane joins formation. The observer pilot visually inspects the Raider, checking for loose panels or fluid leaks that onboard sensors might not immediately detect. The bomber climbs to cruising altitude. The engines settle into an efficient hum, demonstrating the high bypass efficiency required for long-endurance missions across the Pacific or Atlantic theaters. The pilot inputs gentle control pulses. The aircraft responds crisply, validating the digital flight control system's ability to manage the complex aerodynamics of a tailless flying wing. Secure communication links are established with Edwards Air Force Base. Encrypted packets flow in real time, proving the aircraft can integrate into the broader joint all-domain command network. The Raider lines up for approach. The pilot manages energy carefully, as the clean airframe does not have the drag of traditional tails to slow it down. Main tires kiss the runway smoke-free. The trailing link gear absorbs the impact, and the aircraft settles, completing its transition from a manufacturing project to a flying reality. Carbon brakes engage to decelerate the mass. The heat sinks absorb immense energy, bringing the strategic bomber to a controlled stop before the taxiway turnoff. The pilot climbs out to a waiting crowd. Engineering teams immediately download the flight data recorder, beginning the analysis that will refine the fleet for mass production. The prototype moves to Edwards Air Force Base. Here, it begins a rigorous testing campaign, expanding the envelope to verify performance at maximum altitude and minimum speed. The Raider meets a tanker in midair. Validating wet connect capability is essential, as aerial refueling is the key to its intercontinental range and global power projection. Over a test range, bay doors open. An inert munition is released, ensuring the complex airflow around the internal bay does not interfere with weapon trajectory or safety. The aircraft flies against aggressor squadrons. Its internal jammers and passive sensors are tested against real-world radar threats to validate its ability to survive in denied environments. The jet sits in a climatic chamber. Extreme freezing temperatures test the resilience of seals, lubricants, and electronics, ensuring the bomber operates from Arctic forward operating bases. Ground crews practice routine servicing. Evaluating the ease of maintenance is critical to reducing life cycle costs and ensuring high sortie generation rates during sustained combat operations. Back at the factory, the assembly line accelerates. Lessons learned from the first flight are fed back into the digital twin, optimizing the build process for subsequent aircraft. The first operational cadre begins simulator training. They learn to manage the Raider's sensor fusion, transitioning from traditional flying to commanding a sophisticated information warfare platform. The first operational B-21 arrives at Ellsworth Air Force Base. New hangars are ready to house the fleet, designed to protect the sensitive coatings from the elements. The fleet grows in number. The mere existence of these penetrative bombers alters the calculus of potential adversaries, reinforcing the credibility of America's nuclear triad modernization efforts. A Raider executes a long-endurance training mission. Flying continuously for over 20 hours, it demonstrates the capability to strike any target on the globe from the continental US. The B-21 stands ready on the alert ramp. It represents the pinnacle of aerospace engineering, a silent guardian, ensuring peace through the promise of unmatched, undetectable firepower.